Hello students, in this lesson we will discuss about how to convert a decimal number to binary number. So as you know, decimal number system, the base of the decimal number system is how much? 10. Decimal number system base is 10. You already know it because the decimal number system is composed of 10 digits and these are 0 to 9. Okay. Now you must know that decimal number system is also known as denary number system. D-E-N-A-R-Y, denary number system. Okay. And decimal number system or denary number system is a positional value system. Positional value system. Why it is positional value system? Because the place value of a digit in decimal number system always depends on its position. Okay, that's why it is positional value system. And the positional value of a decimal number is always expressed as a power of 10. That means the place value of every digit in decimal number system is expressed as a power of 10. For example, consider this number 659. So 659 is a decimal number, that's why base 10. So if I write 659 like this, then I can tell 9 is placed at units place, isn't it? This is units place, this is 10th place, this is placed at 10th place, and this is 100th place. So these are the positional value. Positional value. So value of this position is 100. That means I can write here 100, the value of this position. The value of this position is 10 and the value of this position is 1. So 100 can be written like that, 10 square, that means 10 to the power 2. 10 can be written like 10 to the power 1. And 1 can be written like 10 to the power 0, isn't it? Because any number to the power 0 is 1. So clearly you can see here that the positional value of every digit is expressed as a power of 10. The positional value of 9, here I can write 10 to the power 0 because 10 to the power 0 means 1. The positional value of 5, here I can write 10 to the power 1 because 10 is 10 to the power 1, and the positional value of 6 I can write here 100 because 100 means 10 to the power 2. So 10 to the power 0, 10 to the power 1, 10 to the power 2, we can write like this. The next digit, if there was a next digit, then we can write here 1000, that means 10 to the power 3, 10 to the power 3, 10 to the power 3 means 1000. If another digit appears on the left hand side, then we can write here 10 to the power 4, that means 10,000, isn't it? So actually the positional value of every digit is expressed as a power of 10. So get back to this number. Here 6 is not actually 6. Here 6 represents how much? 6 represents its place value, and place value of 6 here how much? 6 into the positional value, which is 100. That means 10 square. 10 square, that means 6 into 100, that means 600. So actually 6 represents 600. Now 5. 5 represents how much? 5 equals to here represents, so I can write here implies that sign, and 5 represents how much? 5 into 10 to the power 1. Okay, that's why 50. So 5 represents actually 50, and the last digit 9 actually represents how much? 9 into 10 to the power 0. That means 9 into 1, that is 9. So if you add these three numbers together, then you will get 659, because 600 plus 50 plus 9 equals to 659. So in this way, the decimal numbers are actually we get, okay, by adding the place value of every digit. So it is obvious that in decimal number system, the place value of every digit depends on its position, isn't it? Here 9 is not 90, 9 is 9, 5 is only not 5, 5 is 50. So always depends on their position. That's why decimal number system, you can say a positional value system. Okay. So now this decimal number system we will express. I am taking one question. So I am taking one example here. Suppose I will convert 23, the decimal number, into binary number. So 23 in decimal equals to how much in binary? Because the base I have given here 2. So how much in binary? So what is the rule here? The rule is very simple. You need to divide 23 continuously by 2. Why by 2? Because 2 is the base of binary number system. 2 is the base of binary number system. Okay. That's why you need to divide 23 continuously. And when we will stop? Whenever we will get the quotient less than 2, then only we will stop. Okay. So now here the rule is that here you will write the quotient, and here you will write the remainder. So quotient will be written here, remainder will be written here. So if we divide 23 by 2, here 2 is the divisor. So what will be the quotient? Obviously 11 will be the quotient, because 11 2s are 22. And if I write 22, then what will be the remainder? Obviously 1. So now 11, the quotient that we have got here is more than 2. That's why division process will continue. And the same divisor again, 2. So if I divide 11 with 2, then 5 2s are 10. So 5 is the quotient and remainder is 1. Again 5 is greater than 2. That's why division process will continue. So 2 here. So 2 is the 2 2s are 4. So 2 is the quotient. Again remainder is 1. Now 2 is equal to 2, not less than 2. That's why division process will continue. So 2. So 2 ones are 2. So 2 ones are 2 and the quotient is 0. Now you can see the quotient here we have got is 1, which is less than 2. So the division process is now terminated. And we have to deal with all the numbers like this from here, from the last quotient to the first remainder. Okay. And whenever we will get this, that means the last quotient and this remainder, then these are known as the digits of binary number, equivalent to 23 in decimal. So which one will be the first digit of the binary number and the last digit of the binary number? That means the most significant bit. Every digit in binary number is known as bit. So which one is the most significant bit? That means the first bit. And which one is the least significant bit? Always remember, the last quotient that you will get is the most significant bit. So here 1 is the most significant bit, MSB, and the first remainder, that is the least significant bit. So LSB is this one. So we need to write the number from down to top. Okay, that means the number will be 10111 in binary, not from here to here. That means from up to down. It is from down to top. So 10111. MSB, LSB. Which one MSB? The last quotient of this continuous division process. And which one is LSB? The first remainder of this continuous division process. Okay, so we will write, so 2310, that means 23, the decimal number is equivalent to how much? 10111 base 2 in binary. Is that clear? Let's take another example. Suppose 37. So 37 in decimal equals to how much in binary? So 37, and what will be the divisor? Obviously 2, because 2 is the base of binary number system. So 2. Here we will write the remainder, and here we will write the quotient. So 37, that means what will be the quotient? 18 to the 36. So remainder 1. Next 2. 9 to the 18. Remainder 0. How much? 4 to the 8. Remainder 1. 2 to the 4. Remainder 0. Still the quotient is not less than 2. So division process will continue. 2 ones are 2. Remainder 0. Now the quotient is less than 2. That means the division process will be terminated. So this is the MSB and this is the LSB. So we will write from down to top. So we will write, so 37 base 10 equals to how much? 101 base 2. So in this way, decimal numbers are converted into binary numbers. So that's all for now.